sort of mitigate that issue. The way that attenuated total reflection works is that you have some crystal here, right? And this crystal works almost like a fiber optic, right? And so you have total reflection within this crystal. We haven't talked about fiber optics in this class, but you know essentially what they are, right? You shine light in one end of this long fiber and light comes out the other end, right? The only way for that to really work is that all of the light that goes in has to come out. And so the surfaces on the inside of a fiber optic are what we call totally reflective. Part of that has to do with the angle of incidence that as it goes in. So you lose the least amount of light due to refraction. But it also has to do with the index of refraction between the actual fiber material and its casing. So if that index of refraction difference is very high, you get very little pass through and much more reflection. And so this crystal is made of a material, probably not diamond. It's terbium oxide or something like that. It's a very odd kind of crystal. But it is totally reflective at infrared wavelengths. And you know, this angle that it comes in at is particular so that you get total reflection within the crystal. And so essentially this is coming from our Michelson interferometer. And going out to the detector. And so what we have is we have this very thin layer of sample that sits directly on top of that crystal. For solid samples, it has a little screw that you can just press that sample onto the surface. And so you're sure you get good contact again, so you don't have air interrupting your measurement. And what happens is where the interface is between the crystal and the sample, you get these evanescent waves. So that's what this inset is here, right? And so at the interface, some signal is lost. But the signal that's lost is only the signal that can be absorbed by that material. Wavelengths, or I'll say frequencies, since that's what we tend to talk about in IR. So the frequencies that that sample absorbs will be reduced as the reduced is not a great word there. Will be lost. And so you have this light going in. It bounces a lot of times in this crystal. Each time it bounces, so not just at this first interaction, but at every interaction point. And there's likely a whole lot more than 4 in a real instrument. Each interaction point, you'll have this opportunity for evanescent waves. And at each point, some of that light can be absorbed by our sample. Right? And so those evanescent waves will only be absorbed if they are of the right wavelength frequency. And so just like a regular absorption experiment, we see some loss of signal due to that. Now, you tend to get much less absorption this way, just because those evanescent waves are not all of the light, right? Not all of the light is passing through the sample. Most of it is getting reflected back into the crystal. And so that's why in reality, it's set up as bam, 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 and then it's out. In reality, this would go back and forth a few times, based on what the geometry is. So that you actually hit that sample, hundreds of times probably, before it actually exits the crystal. And so you essentially lengthen your path length that way, because you're not interacting with the sample. You're not going through the sample, you're just interacting at the surface. That's another reason why we need to make sure that the sample is pressed flat against it. And so with a liquid, you don't have to worry about that too much. But with a solid, you have that, it's called an anvil that presses down on the sample to make sure that it touches that. So the sample touches the crystal as much as possible. You get as much contact as possible. And so on the IRs that we have, they're very modular. You just pop out the holder that is for the salt plates, and then you pop in the module that has the ATR crystal in it, right? We're not changing out the interferometer or anything like that. You just pop out the crystal for the plate holder. And if you're a real doofus like this guy, then you wonder why you're not getting any signal for like 10 minutes and realize that the module with the crystal has caps on the side so that thing stays nice and sealed. And if you don't take those off, no light can get in. And so no signal for 10 minutes trying to figure out what was wrong. We figured it out. Okay, that's chapter 11. That's IR. Questions about ATR? Okay. So we're moving into chapter 12. Let's get things set up here. All right. So in Raman spectroscopy, again, this is a technique that is sort of a complement to infrared. In Raman spectroscopy, what we're looking at are still vibrations by and large, but we are focusing in on sort of a different variety of vibration. So some from our textbook, some interesting images, right? The one on the right is looking at artwork. You can, at infrared wavelengths, these are what we call penetrative wavelengths. You can look at more than just the surface, right? You and I can only look at the surface of things because the wavelengths that our eyes register only are small enough that they bounce off of most surfaces. But longer wavelengths can penetrate deeper into materials, and so infrared wavelengths can sort of help us look below a surface. And so on the right, we're looking at artwork. A lot of times they look to see, was this painted over something else? Is the original sketch that they did in pencil below here? Because those things will have different infrared signatures. And then on the left, this is a biomedical use, right? This is not a needle going into this guy's arm. It's a Raman probe on the skin. Again, at these wavelengths, we don't have to look at just the surface. We can go a little bit deeper into the material. In this case, that material is human. And so we can maybe look for a particular cancer agent, maybe a metabolite of some disease. You can look for lots of issues, lots of different things. And so what is Raman scattering versus Rayleigh scattering or Raleigh scattering? And so Raleigh scattering is sort of what we normally think of when we talk about scattering. When we looked at olive oil last week and we said, there's no scattering here. It's all fluorescence. We were talking about Raleigh scattering. And so this picture here just has some laser pointers, and you can actually see the laser beam because there are things in the air that are scattering that light. And so Rayleigh scattering is one wavelength in, one wavelength out kind of thing. Sometimes it's hard for me to even think about it as an absorption event, although that's how they are describing it when comparing it to Raman scattering. And so if you have some particle, right, even if it's not necessarily a molecular particle, it will absorb a photon and then give out a photon of exactly that same energy. And the reason it's the same energy is because these are virtual states. Right? We're not going up to an actual S0 or an excited vibrational state. We're going up to some state that doesn't really exist, right? And so that's part of the reason why I say it's kind of hard for me to wrap my brain around Rayleigh scattering actually being absorption emission event. You absorb a photon, you emit a photon on the same wavelength because you're not going into an electronic state. You're not losing any energy to vibrational relaxation. You're just one in, one out from this virtual state. In Raman scattering, the difference is that you actually have some energy loss or energy gain due to the fact that we go from one vibrational level in the ground state up to this virtual state and then down to a different vibrational energy level. And so there's two kinds of Raman scattering, Stokes scattering and anti-Stokes scattering. And so in Stokes Raman scattering, right, we have this black absorption event, and then we have this blue photon that comes out, and of course this photon is lower energy. Right? So that lower energy photon is what gets scattered out. However, in anti-Stokes Raman, notice, well, this image from our text didn't do a great job of it, but these black lines are supposed to be the same length, right? This gap between the virtual states up top is a little bit wider than it should be. But all the black arrows should be the same energy. Wavelength, frequency, however you want to think about it, right? And so in an anti-Stokes Raman scattering, your molecule is already in an excited vibrational state, right? It's not in the ground state, it's in an excited vibrational state. And so when it absorbs that photon, it goes into a virtual state that's that much higher in energy than the virtual state for a Stokes Raman event. However, when it comes back out, when it relaxes back down, probability tells us that we will get relaxation down to the lowest vibrational state, and that would give us anti-Stokes. Okay? If we went from an excited vibrational state up to a virtual state and then back down to an excited vibrational state, that's still, that would be Rayleigh scattering, right? If we went back down to exactly the same vibrational state, because it'd be the same energy in, the same energy out, right? So if we change vibrational states, that's when it's either Stokes or anti-Stokes. Stokes, if we emit down to an excited vibrational state. Anti-Stokes, if we emit down to the ground vibrational state. All right, and so in this little graph here, we see Rayleigh scattering in the middle. And so this is also our excitation wavelength, right? And in reality, this is enormous, right? This is much bigger than, 2 or 3 times the Stokes peak, which is what it shows here, right? In reality, this is 1,000 times bigger than the Stokes peak, right? But then at this higher wavelength, lower energy, right, we get our Stokes shift, and lower wavelength, higher energy, we get our anti-Stokes shift. Again, I don't know who did the figures for the first edition of this textbook, but usually those shifts are the same. And in this figure, at least, those shifts are not the same, because this energy difference is the only difference between those two, um, between Stokes and anti-Stokes, and they should be the same. Right? Whether you're going up from it or down to it, it should be the same. So we have our Stokes and anti-Stokes. The reason that the anti-Stokes is a smaller peak, a less intense peak, has to do with that Boltzmann distribution that we saw in chapter 7 when we talked about AA, right? And at room temperature, it just so happens that most molecules are in the ground vibrational state. And so most of the Raman that happens is Stokes Raman. We do get a small amount of anti-Stokes Raman. The more we heat our sample, right, the more we're going to shift that Boltzmann distribution to an excited vibrational state. And so we could increase our anti-Stokes intensity by heating our sample. But usually what we care about is the Stokes shift. Okay. So this whole idea of virtual states, again, it's kind of, it goes against everything else I know about quantum theory, right? Because you go from ground state to excited state and there's nothing in between. But Raman theory is essentially telling us that, well, yeah, kind of, there is something in between, but they don't really exist. So it's hard for me to wrap my head around and connect it to quantum theory, but that's the way it works. Right? Questions about these diagrams before we move on? Okay. So, we said that it was a lot like infrared spectroscopy, infrared vibrations, but there's differences in what's considered Raman active and infrared active. Did you talk about this in PChem2 at all?
We talked about it in inorganic.
Oh.
Okay.
Well, I guess, yeah.
I know that you talk about some selection rules, maybe rotational selection rules in instrumental, 2J+1 and all this business. And so for Raman, the selection rule is that the vibration must change the polarizability of the molecule. And so these are two diagrams, again, from our text that help sort of explain what polarizability is, right? When we think about something being polarizable, that just means that it has a lot of electrons that are very spread out, right? The more spread out those electrons are, the more polarizable that molecule is. And so if we have, something like, just for example, since we know the structures from our fluorescence chapter, if we have anthracene, right, that's those 3 fused rings together, we have lots of extra pi electrons that are moving all over, and it's a longer molecule than, say, benzene, which is just a single ring, right? And so not only do we have more electrons, but also they're spread out across a larger space, and so anthracene is much more polarizable than benzene is. When we talk about it in terms of a vibration, we're talking about which vibrations spread out those atoms across more space. And so at one point of that vibration, the molecule is more polarizable because those electrons are more spread out. And at another point in that vibration, those atoms are closer together, and so that molecule is less polarizable, right? And so in the diagram here on the right, we have our equilibrium geometry, and we have that in 3 places. And then at one extreme of our vibration, those molecules are very far apart. And so it's very polarizable at one end of the vibration. And at the other end, those atoms get very close together. And so that molecule is much less polarizable at the other end of that vibration, right? So if we think of a vibration as going back and forth, at one end, it's going to be very polarizable. At another end, it's not very polarizable. That change in polarizability is what we look for in Raman. And so this would be a Raman active vibration. Okay. CO2 is another, this is using a more real life example, right? In this symmetric vibration, this is exactly like what we saw before, right? We have the molecule where at one end of that vibration, those atoms, those oxygen atoms are very far apart from the carbon. At the other end of that vibration, the oxygen atoms are very close to the carbon. And so this one would be Raman active. This antisymmetric, at one end of the, I'm going to use my head as the carbon atom. At one end of the vibration, we have an oxygen close and an oxygen far away. At the other end of a vibration, we have an oxygen close and an oxygen far away, right? Those oxygen atoms switch which one they are, but the actual molecule looks pretty similar on both ends of that vibration, right? And so our polarizability really does not change in that case. And so this is not Raman active. And in this last one, again, using my head as carbon, at one end of our vibration, our oxygen atoms are up here. At the other end, our oxygen atoms are down here. Again, that molecule looks very similar. It's just flipped in space. And so the polarizability, that electron distribution, doesn't actually shift very much. And this is not Raman active either. In chapter 11, I kind of skipped over it, but now is a good time to bring it back up. When we think about what's infrared active, the selection rule for infrared active is not changing polarizability, but changing the dipole moment, right? And so when we think about dipole, right, remember we're going to look at the positive side of the molecule, the negative side of the molecule, and see what shifts. And so CO2 normally is nonpolar. Those two dipoles cancel out. So let me shift colors here. So in a normal state, CO2 is nonpolar. Those two bond dipoles cancel out. We don't have a molecular dipole. If all I'm doing is lengthening those bond dipoles, but in a symmetric fashion, does my dipole change? Not at all, right? And so this first vibration, the symmetric vibration, is Raman active, but not infrared active. Okay? And so we will not see a peak in the infrared spectrum for the symmetric CO stretch. In the antisymmetric stretch, we have a very large bond dipole for one side and a relatively short bond dipole on the other. In this case, right, in this case, the bond dipole is pointing pretty much that direction, right? Because going from the carbon to the oxygen, and there's very little over here to cancel out, and so most of it's going that way. But when these two move, my dipole switches. Right? My dipole is moving back and forth, and so this one is IR active. Right? And then, of course, the last one, if our dipole is changing direction by going from looking up to looking down, this is also IR active. Right? And so again, for IR, we need a change in the molecular dipole.
Isn't there That mutual exclusion rule, is that with if it has the center of inversion, like it can only be one?
Yeah, if it's a centrosymmetric molecule, so symmetric about the central atom, like CO2, then there is this rule that it can only be IR or infrared, right? It can't be both. That's a nice shortcut, but we find very few molecules in real life that are centrosymmetric, and so in my opinion, it saves you a little bit of time, maybe, but often it's just an extra thing for you to remember.
Fair.
Okay. All right. Our textbook does have some nice, a nice explanation about polarizability and how to think about that. If I haven't covered that in depth enough for you, so do take a look in chapter 12 if you're having some difficulty sort of figuring out what this polarizability business is all about. So, Raman instrumentation, and what does it actually look like? The biggest piece of Raman that we're interested in, that's different from an infrared, is going to be the source, right? In a source, in an infrared instrument, what we're looking at is sources that generate infrared wavelengths. In a Raman instrument, we're really not all that interested in infrared wavelengths because we don't have to go to a vibrational state. We're trying to go up here to some virtual state. And so we're actually trying to get out of the vibrations, but not all the way to the electronic state. And so let me draw here just a little box diagram. Also, because we're looking at scattering, what's our orientation of the source and the detector going to be?
The detector's not going to be like directly across from the source.
Yeah, absolutely. And so we have our source into our sample. We don't have a monochromator here because almost always, in almost every Raman instrument, this is a single wavelength source. And again, almost always a laser. From our sample, then we can go into a monochromator because again, we're interested in that emission. Right? So this is almost like a fluorescence experiment. We're looking at not fluorescence, but scattering. And scattering is isotropic. Again, it occurs in all directions. And so, it doesn't matter where we put that monochromator as long as we don't get any source light. From the monochromator to the detector. Right? And then off to the computer, the stuff that I don't care about. Okay. And so this looks very, very similar to what we saw in a fluorescence instrument, right? The only difference being that in a fluorescence instrument, usually we have, in a research grade fluorescence instrument, we have two monochromators, right? We're able to select our excitation wavelength. In Raman instrument, we almost never have that option unless we have multiple lasers. So lasers, I haven't really talked about a lot as a source. If anybody is interested in doing lasers as your final oral report project, let me know. I told Savannah she could do it if she's interested, but if she's not interested, it's up for anyone. And so, lasers have this single wavelength coherent output. They're very strong, intense light sources at a very narrow bandwidth, right? And so, again, single wavelength, intense, with a narrow bandwidth. Okay. because we're interested in looking at those Stokes and anti-Stokes shifts, and because there is such intensity from the Raman scattering, oftentimes somewhere along in here, right, you'll have this notch filter, it's called. And a notch filter, if we look at wavelength versus transmission, looks something like that. We had a different term for this when we talked about filters in chapter 3. Who remembers? Long pass, short pass, band stop, band gap. So it's not a high pass or low pass, right? Because it's both of those, really. So are we stopping this band or are we letting this band through?
Letting it through. Yeah.
So if this is transmission, everything gets through except this. Right? And so this is a band stop filter, is another way of thinking about it. So notch filter, band stop filter, those terms are interchangeable, right? But it's going to be centered at our laser wavelength. So A, we don't get any scattering from the laser, which hopefully we don't really have anyway, since we're at 90 degrees. But B, we want to make sure that we don't get any of that Raleigh scattering. Remember, Raleigh scattering is scattering at the same wavelength that we excite. Some issues with Raman instrumentation. The biggest issue that we run across is this issue of fluorescence, right? Because we are using most of the time visible wavelengths to excite our molecule, we have this issue where we could be exciting the molecule into some excited state rather than into a virtual state, right? And so we have to strike a balance between exciting it so much that we're getting into the excited states, but not exciting it enough that we're staying in the vibrational states, right? And so we have to balance between exciting too much, which puts us in a, an S1 state, or not exciting enough, right? Which would put us into a I'll put in X state, right? So an excited vibrational level. We want really something in between those two. We want to be not in an excited vibrational level or in an excited electronic level, but to be in a virtual state, right? And so this example from our text is Zantac. And so if you look at the tablet, a Zantac tablet, if you look at a low wavelength, you get this very broad fluorescence emission rather than a nice Raman spectrum. Remember, Raman and all vibrational spectra are going to be very sharp peaks because those energy levels are very well defined. And those transitions are one energy level to one other energy level. In molecular transition, remember, we're going from the ground state to any of the excited vibrational states in the excited electronic state. And then we go back down in fluorescence, we go to any of those excited vibrational states in the ground electronic state. And so fluorescence and absorption very broad relative to infrared and Raman. And so at 532 and at 785, we get this relatively broad fluorescence. But then once we get down to this is an infrared wavelength, but it's in that near infrared, right? It's very close to the red end of the visible. And that 1064 nanometer is it's the first natural frequency of an Indy YAG laser. Again, I'm not going to get too far into lasers. My graduate work was all lasers all the time, man. Our lab did not look like a chemistry lab. It looked like a laser lab. We had one hood for 7 people. So the 1064 is this sort of near infrared wavelength. It's the fundamental wavelength, fundamental frequency out of a YAG laser, and gives us a nice Raman spectrum with these relatively sharp peaks. And so again, we handle this fluorescence problem by just lowering the energy of our laser. We can't lower it too much or else we'll get down in the vibrational states, but lower than what we might excite into a electronic state. All right, so some neat applications of Raman. Raman is a very portable device. Lasers, they make diode lasers now, which are really, the size of a dime or something. And so, you don't need a lot of equipment to do a Raman experiment. Because you don't have like a Michelson interferometer in Raman, it's much more portable than an infrared. Almost like the small UV vises that we have used in lab, the little the box ones, they have a diode array monochromator, and so you don't need fancy moving parts for your monochromator. And so Raman can be made pretty robust in a handheld device. And so the one on the left there, obviously that's a handheld device. The one on the right is an interesting, it's a probe. It's almost like the one we saw on the first slide where you were looking at your skin. And the way that works is that you have your excitation wavelength coming in. Okay? You have a band pass filter so that only your wavelength gets through. This dichroic is the same as a beam splitter. Okay. And so what happens is you focus in your excitation beam on whatever your sample is. The scattered light comes back exactly the same direction, but that beam splitter splits off any, splits off both the Raleigh and the Raman scattered. So we get both of those back. But here we have a long pass filter. And so with a long pass filter, are we going to get both Stokes and anti-Stokes? No, we're only getting one of those. Which one are we going to get if it's a long pass? Which has a longer wavelength, Stokes or anti-Stokes?
Stokes.
Yeah, Stokes has a longer wavelength. Remember, Stokes is the more intense version of scattering. And so, that's really the one that most people focus on. And so it's fine to have a long pass filter instead of a notch filter, that band gap, band stop filter. And so you get this Stokes only, right? Certainly reasonable for a handheld device. This is another application of Raman. And so you can see here that they're looking at fat cells, and so these fat cells light up nicely in this image here. And these are the fat cells. And at least from my eyes, this differentiation between the vessel and the connective tissue is sort of lost, right? Because it all just looks like green dots to me. But they can sort of easily identify certain types of materials. In this bottom one, they are looking at yeah, in the bottom one, they're looking at cancer tissue, and so they're pointing out this highlighted region. So here is here. These two little guys are these packets here, and so they're trying to point out that this green, all these green dots that you see, are highlighted in this pink area. So, you know, maybe they have added a tag, maybe that's just the Raman signature for those particular kinds of cells. Again, the top is non-cancerous, the bottom is cancerous. This is an example from our text. I didn't read the paper that goes along with it. Maybe green is good. You see no green in the bottom. I don't know exactly. But the point is they can differentiate between different types of tissue based on Raman signatures. All right, so one way that Raman can be used, especially in a biological setting, is through microscope Raman. Similar to that handheld probe that we were looking at, except it focuses it down to a much finer beam. And so you end up being able to look at, you know, several square micron sized patches of a cell or of you know, whatever it is that you're interested in, some tissue, right? And so again, this is just like a box diagram here, but your laser comes in and it goes into the microscope. Let me change colors again. Right, your laser goes in the microscope and down through your optic onto your sample, and then the scattering comes back up through, hits that notch filter. That notch filter is going to block out any Rayleigh scattering you have, and then goes into your monochromator, your grading, and then they're using a CCD instead of a diode array, but it acts essentially the same way. And so you're able to focus down that point, that analysis zone, that analysis region, to a very very small part of your sample. This can also be useful for materials analysis. You know, if you're dealing with polymers and you have you're looking for defects, any defect in your polymer sheet is going to give a different infrared signature, different Raman signature than the bulk material.
Dr. Davis, is that green line the Raman scattering?
Yes, sir. Okay. The last thing to talk about is SIRS spectroscopy. This has gotten a lot of interest in the literature. And so when we look at surface enhanced Raman, what we see is that if we have a not smooth surface, right? And so the term that they use a lot of time is nano rough. Because to your finger and my finger, it would be smooth. But at a nanometer scale, it's not a smooth surface, right? It's not atomically smooth. There are these jagged edges. Some early SIRS substrates just used like nanospheres, actual just coat a surface with these little spheres. They have been able to make more refined shapes since SIRS began. And so this image shows some little triangles. I don't know if that's realistic or not. But on this surface, there is some interaction, and it's not 100% clear what it is. There's sort of two leading theories right now. One is that you get a charge transfer complex between the metal and the molecule. So if you think back to a physics class, maybe you talked about semiconductors and how you had your two bands with the band gap in between, right? A charge transfer complex is a similar thing, except the lower energy band is one molecule or one substance, and that conduction band is a different substance, right? And so they form a charge transfer complex, even though they're not the same material. And so the thought is that that sea of electrons that are in this metal form the lower band, and then the molecule itself is forming the conduction band. And so when the light hits it, that charge transfer complex is able to sort of intensify the effect. And so surface enhanced Raman, this enhancement, right, is on the order of 10 to the 10 maximum, right? Enhancement. That's huge, right? 10 to the 10 is like saying, oh, I have $1. Oh, I have $10 billion, right? That's a huge enhancement. And so we're able to actually do Raman on single molecules these days because of SIRS enhancements. Right? The other theory is that we're forming surface plasmons. So when you hit a metal surface, especially at the nanoscale with light, you sort of focus that energy on that surface. And once you focus that energy on the surface, then it's more able to excite that molecule, all of the molecules in the sample, to an excited virtual state. And so by forming those surface plasmons, you're actually helping every molecule in your sample absorb, rather than just those that happen to be directly in the light path. You're helping all the molecules in your sample, everything that's on that surface, absorb light. And so you increase your enhancement, your signal. So maybe you've seen SIRS if you've been cruising optical literature. I don't know. I don't know that that's what many of you do in your free time. Anyway, that's it. I hope you enjoyed chapter 12. I'll see you later.
Yeah.
Bye, thanks.
Ta-ta.